Hello and welcome to the AQUALIS Sustainable Water Compliance Summit session, Coastal Erosion, Causes, Datasets, and Mitigation. I am Katie Johns, Editor-in-Chief of Stormwater Solutions. To begin, I'm going to go over a little bit of housekeeping. First, if you have any technical difficulties during this event, please put your question in the questions window and our technical experts will help you out. Additionally, we welcome your questions during this session and we'll answer as many as we can during the Q&A following Brian's presentation. But you can send in your questions at any time, no need to wait until the end. To do so, just type your questions into the question window on the side of your screen and hit submit. Also, please note that today's event is being recorded and you will be notified by email when the archive is available. At the conclusion of the webinar, you will receive an email with a link to download your certificate, which can be used to submit for credit with Stormwater University or serve as one personal development hour for attending today's webinar. Certificates will be sent to attendees who viewed the session for a minimum of 50 minutes. For those viewing the session on demand, you will need to complete and pass a short quiz at the end of the session to receive your certificate link. And now I'd like to introduce you to this session's speaker, Brian Caulfield, who is the Coastal Systems Resilience Discipline Lead at CDM Smith. Mr. Caulfield is CDM Smith's Coastal Systems Resilience Discipline Lead. He has over 2 decades of experience specializing in coastal flood hazards. He specializes in hydrodynamic modeling, wave transformation, coastal structure design, and sediment transport. So with that, Brian, the floor is yours.
Thank you, Katie. I appreciate the opportunity to speak here to everyone as part of this summit. And so, as mentioned, my name is Brian Caulfield. I'm with CDM Smith. I am the Coastal Systems Resilience Discipline Lead. I'm a board certified civil coastal engineer. And as mentioned, I've been doing this for the last 25 years or so, and kind of focusing on the coast. Coastal engineering is a unique field, or kind of a small field, that is a part of really kind of the civil engineering program. We tend to be water resources engineers that have additional specialization related to understanding coastal hydrodynamics, sediment transport, and we also dabble in kind of understanding of atmospherics, because we need to understand the storms that kind of drive what's happening in the nearshore zone. So as kind of mentioned, I'm going to be talking about beaches and the focus of what those beaches are, kind of the causes for erosion, some of the mechanisms of erosion. We'll talk about where some of those data sets for coastal erosion exist, and then ways to minimize and mitigate erosion. The importance of beaches. This is from a 2004 report from Dr. James Houston. He's with the U.S. Army Corps of Engineers. He looks at the economic value of beaches. And in 2004, there was this understanding that beach tourism was about $250 million. And we have greater than 50% of the U.S. population living in coastal counties. He did just update this number for a 2024 report that was submitted as a journal article in Shore and Beach. That $250 million is still kind of in line with current understanding, but those were through the COVID years. The expectation is those numbers will probably increase when we get back to a more regular understanding of usage of the beach. Additional groups that look at kind of and value our beach systems is NOAA. They are from the Department of Commerce. These are the top 5 states for gross domestic product where ocean tourism and recreation contribute. You'll notice, of course, California, Florida, New York, Hawaii, states that you think you would see. Then Illinois pops in there, and it's a realization that Illinois, of course, is on a Great Lake. And so, these 5 Great Lakes have similar physical processes, wave energies, and coastal erosion concerns. And so they too are considered when we look at and try to understand their damages. I'm actually unique in the field of coastal engineering, as I did my graduate and undergraduate work at a Big Ten school. So, of course, I have understanding of Great Lakes. It was until I got into the work world that I had to realize what a tide was and understand its impact on coastal erosion. So what are the function of beaches? They tend to act as buffers from storm waves. They will play a role in flood control. There are places for wildlife habitat. And as we've been talking, they're, of course, spaces for recreation. From a storm wave buffer, there's something to understand with respect to waves themselves. As the wave energy is developed in the offshore zone, they interact with the bottom and the waves begin to break and shoal as they move into the nearshore area, and then finally hit and dissipate their energy completely on the beach. And the wide beach can act as again, an energy buffer. It's where you want to dissipate the wave energy from happening. You'd rather it happen on the beach than to actually get dissipated as it interacts with any kind of infrastructure just behind the beach, whether it be roads or telecommunication or homes. And so these wide barrier beaches are what we hope for to act as a kind of a storm wave buffer. They're the places where we want to see the wave energy decay. They also work in flood control. So, if we have these low-lying beach systems or in the barrier beaches, if the beach isn't there, then the water can just kind of flood right into back bay barrier systems. This happens to be, this is called Shore Road. It's on the south side of Falmouth, which is on Cape Cod. And that town, when you have a high kind of wave event or even just normal wave event, because you're looking at flooding within in our Vineyard Sound, the wave energy just kind of can go over the road, and you've got to come back and fix that road. And so these beaches, when you have them, can act to kind of push that water further away from impacting on the roads themselves. Then, as I mentioned, wildlife habitat. This is an important factor of any beach system. That the bird on the left is a piping plover. It's kind of the bane of most coastal engineers. The piping plover will limit the window in which you can work on a beach. So you can only place sediment on a beach at certain times because you can't interfere with piping plover habitat as the birds are nesting and mating. The birds also have certain slopes that they prefer to walk on when they're doing their foraging. And so you have to limit the slopes you're using when you're doing your engineering design for a beach nourishment profile. And also the birds prefer to nest away from large, dense vegetation because that vegetation is where their predators can hide. And so they want to make sure that they're far enough away. So they usually nest in overwash fans because they have the ability, it's low slopes and they're farther away from the vegetation. But of course, we as engineers want the vegetation because we want to have it help stabilize the dunes. And we'll talk about that more later. And then there's also other flora and fauna you'll tend to see in some dune systems. You'll see deer quite often in the dune systems, which is not something you tend to think of. You tend to think of deer as being more in vegetation, like in treed areas, but you'll often find them in low kind of the dunes and the forest that surround those dunes. And then, of course, as I started off with, there's an understanding that the beaches are valuable to us for recreational activity. Those wide sandy beaches are where everyone wants to go this summer and enjoy themselves to get away from the heat of the inner city. You want to be able to dip your toe in the water and work on your suntans. And so beaches are a valuable recreational commodity for everyone, but they want to use them. Let's look at kind of the causes of erosion. So when we look at the causes of erosion, of course, the important one is storms. It's the waves and coastal flooding. But there's also seasonal beach changes that you may not be aware of that you may think is erosion, but it's actually just a natural processes. You see the loss of sediment supply impacting coastal erosion. You see how waves interact with the nearby structures. And then finally, sea level change also influences our erosion rates. And we'll kind of talk about each one of those factors now. So, storm wave erosion, this is the important concept really to understand about sediment transport in the nearshore zone, is that sediment transport rate, the equations we use are all based on wave energy flux or power, and that scales as the square of a breaking wave height. So the breaking wave height is usually the wave height that's where you see breaking when you're looking out into the water. A lot of times that breaking wave height might be, say, if it's 3 feet, well, then if you square that, of course, it's 9. But if it's a 10-foot wave, which is something that's happening in a storm, that's now 100, right? So you're seeing a factor 10 difference between a 9 and a 100. And so that's kind of what drives this sediment transport rates and the differences. And so the higher the wave energy, the more sediment the wave is capable of carrying, and also the larger the grain size can be that the sediment is going to carry. So in higher wave energy shorelines, you will tend to see larger grain sizes as the primary beach. So like if you go out into Oregon and Washington, you might see cobble type beaches. And so cobble is going to be a nice, softball sized sediment, which isn't enjoyable for walking on and bare feet or recreating on. but it exists because of the wave energy that's hitting that portion of the shoreline. And then when you get into some of the lower wave energy environments, you'll see nice, pristine, white sand beaches like in Florida. And while those areas are subject to high wave energy, it's just on the average, they have low enough wave energy that you're not really seeing, or you have the ability for these smaller grain sizes to sit there and fall out of transport. And so it's important to understand that the waves, of course, are the primary factor when drawing erosion. Flooding, though, also can play a role. And so if you're in a low barrier system, if the water can get over the top of that barrier, it will start to flood on the backside. And then you start looking at waves, or you look at water moving with velocity. And under those velocities, of course, the sediment grains can be moved around. Quite often, the grains are either pushed further back, up onto the roads in the infrastructure setting, like on most shore roads. Oftentimes, though, it can also be filtered back out into the littoral system. So that's the sediment transport along the shoreline. And you have the ability to pull those grains offshore. And so you begin to have erosion because of the storm flooding as well. You also have these seasonal beach variabilities. And as I mentioned, the seasonal beach variations, oftentimes when you see these, you tend to think of, there is erosion that's happening. But in reality, it's a natural process. During the summer, you're going to have a beach berm, and that's where everyone's going to be sitting and recreating. But during the winter, when you have higher wave energy, the high wave energy starts to hit that beach berm, and it starts to pull those sediments offshore and forms offshore sandbars. And then during the summer, those sandbars will move back and meld back into the beach. And so kind of the sand in a setting where we tend to have a good equilibrium of sediment available, then sand will move offshore and back onshore. In most settings, though, the sediment supply has been limited. And so those sandbars sometimes get too far offshore and the sand can't move back onto the beach in the lower quiescent summer months, or because of just the loss of sediment volume over the course of years, the sandbars get smaller each year and they're not able to kind of bring enough sediment back to the sand berm. What some communities will actually do during the winter is they will bring out bulldozers and they'll push the berm up in towards the dune. So that way, instead of the sand being moved offshore into the sandbars, it's staying kind of in the beach area. And the thought process of those communities is that they're kind of mitigating, the rate of erosion that could potentially happen in the early parts of spring, because the sand is closer to the beach, which is where they want it to be a wide natural beach feature to reduce the wave energies. And so that is something we tend to see quite often. But if we let it go under natural processes, the sand should move offshore and come back onshore through cross-shore sediment profile variability and how sediments move in a cross-shore profile, not just in the alongshore profiles. So if you're out on the beach this summer and you're standing there and you're on the beach and then you kind of wade through ankle deep water out to a sandbar, that's usually the sandbar being moved back. It's the sand that was moved offshore during the winter, making its way back onto shore. So it's just kind of the natural processes as they happen. We've been living on the shoreline for quite a long time, and we've built a lot of infrastructure along that shoreline to maintain where we've resided. So we've built vertical seawalls, to act as erosion barriers. And then by trapping that sediment behind those seawalls, we're not allowing the sediment to get into the system and be transported along the shoreline. So you're beginning to starve the littoral drift of its source. And when that begins to happen, you'll see profile down cutting, as you see in this image on the left, where you're starting to see the exposed foot of a seawall. And you also will see that, of course, the grain size variations. You'll see a lot more cobble in the nearshore zone and gravel, because of the fact that the smaller grain sizes are being able to be transported at lower wave energies. And so they are moved from that area into a different space. And you'll see then just kind of this natural gradation due to the way wave energy results in moving sands. The image on the right, that's Hull, which is a community in Massachusetts. It's kind of the barrier of offshore of Boston. Sometimes if you ever fly into the Logan Airport, you fly up along Hull. It's on your left-hand side before the plane turns left to do the landing into Logan. But the Hull is a series of headlands with sand in between. They've also been, they've done vertical structures along that shoreline because of the road. And you can see it's a nice wide beach. That's also because of the fact that you have a 9-foot tide range in that area. So with 9 feet, you kind of expose a lot of the barrier beach itself. But it's also, it's been starved because you've not been able to bring the sediments from the upland back onto the shoreline. But what works within the whole area is you're between these two rocky headlands, and so the beach just kind of sloshes back and forth between those headlands and is in a stable nature. But at the same time, other background effects begin to reduce the amount of sediment, and the beach is narrow, and so you have to sometimes bring sand in for a nourishment type project. So how do the sediments interact with structures? So the way the waves interact with coastal structures that are perpendicular to the shoreline, we call those structures groins. That's what you see on the left-hand side. It's a wooden groin. The waves will hit the structure, and then on the lee side of the structure, the wave energy is less, and so with less wave energy, the sediment should fall out. And then they also act as just a trap because you don't have the ability for the wave energy to continue to carry through the groin itself, and so you get these accretional fillets and erosional fillets. But more often, what you tend to see when you look at a groin is you'd see a groin field. So there's multiples of those groins, and the idea is that the downdrift groin's accretional fillet is large enough to cause accretion on the backside of the other groin that's upstream of it or updrift of it, so that you don't end up with like these erosional patterns. So by nature, these groins are supposed to interrupt and limit the sediment supply, but allow it to fall out. It's not something that's in favor right now for coastal projects. You usually don't see a groin being built because of just the permitting hassles. What you do tend to see, though, is a lot of times if groins are being permitted, they tend to be hybrid in style. So they'll have lower profiles. That means we'll lower the elevation at the top of the groin to allow for sediment to go over the groin during certain wave energy events. And sometimes that's actually on the beach side. So we're letting the sediments move on the beach side, which is where you tend to see the erosion. And then also they'll do like lower profiles or slats sometimes in the offshore edges to allow the sediments to move throughout there. So instead of having the sand get pushed into an offshore area and have this bypassing, then they'll actually allow the sand to move through the groin itself. The other thing we talked about were just, when you have these structures on the shoreline, that are designed to limit erosion, those that are built well will limit erosion, right? They're going to stop the sediments from moving up and being impacted by the wave energy. But by that, you're beginning to starve the sediment supply. And so quite often, in permitting, they require you to consider the amount of sediment that you entrap on an annual basis. And you may be asked to actually place that amount of material in the nearshore zone on an annual basis as a, kind of a mitigation measure. So sometimes that happens in your permits. If you try to build some of these structures, then there may be a requirement that you offset the fact that you've built the structure by bringing sand back in. And lastly, as I mentioned, sea level change is also another factor that is, kind of a background happening in coastal erosion. The image on top, that's the map of sea level trends across the United States and Canada from NOAA's website. The arrow pointed up represents sea level rise. Arrows pointed down are sea levels going down. The sea levels are going down, as you can see, they tend to be in the northern part of the continent. That's a result of the fact that you have glacial uplift happening there. So as the glaciers have melted away, you begin to see that the isostatic rebound, you're having the continent kind of go upwards. And so the rate at which the continent is moving upwards is equal to or greater than the rate at which sea level is increasing in height. And so it's in a relative sense, it looks like sea levels are going down. But as you look across most of the continental United States, you see the trend of sea levels going up. That includes, all along the Pacific, Gulf, and Atlantic coastlines. The bottom image is the observations of sea level at Wilmington, North Carolina. That's a gauge station I just picked up out of curiosity. You can look over the 100 years at which the gauge has been observational. You can see how there is an upward trend in sea levels. It's on the order of about 30 centimeters over the course of those 100 years, which means in the last 100 years, you've had 12 inches of increase in water depth in those areas. So if you think of a 12-inch vertical rise, there has to be some commensurate horizontal space that's been taken as well. And so, because there's not all just vertical shorelines, you have kind of naturally sloping shorelines. And so as the water has moved upwards, it's also moving inland, and then it basically is impacting areas of shorelines that weren't acceptable to water interactions before, which means sediment grains are being moved that may have been deposited there earlier under a more quiescent time. And so, in essence, the shoreline is just kind of rolling back on itself. But if, again, we've built in these environments, we've already squeezed how much where the water can move in a horizontal space. So as you see sea level rise, you can see also that erosion is happening as the water levels, or as the beaches adjust to the new water levels. And then the erosion kind of varies by shoreline type. And so whether it's a mainland beach or barrier beaches or a coastal bank or of course around structures. When we think of the mainland beaches and dunes, they're usually, if it's a dune system, it's a non-cohesive sand. It's been placed by aeolian transport. Aeolian means wind dominant. So the wind picks up the smaller sand grains. They hit the grasses that are part of the beach system or dune system, and then they fall out and you result in kind of a dune height growing. In some instances, though, like you don't have a dune, you may have a coastal bank. So that might be some sort of glacial depositional layer that's underneath the sand that's kind of a surface layer. And those cohesive materials act completely differently when they erode. They tend to be more chunky, like they come out in groups. So it might be like a peat layer from some remnant bog or marsh system that used to sit there. So they're going to come out in chunks and not in a nice little angle of repose at the end of the day that you end up quite often with sand grains. So you'll see that when you look at barrier beaches, just the whole complex tidal hydrodynamics also starts to play a role, because you don't just have sediment transport of the longshore processes, but then you have usually these inlets that get formed when the barrier beaches breach, and you have then flood shoals that get formed. So that's when the tides flood in and bring sediments into the floods or into the bays, and then it just continues to fall out. And it's a very dynamic system. So this is the Chatham Barrier Beach, which is out on the outside of Cape Cod. So that's where you tend to see all the Shark Week videos being taken nowadays. But it's breached quite often in the recent history. But it's a natural breaching. It's expected to happen. They know it's going to happen. It breaches in the narrow spots. You can then see kind of the three imageries top to bottom on the left. You have this then, the formation of a breach, at which then sediments begin to fill in. It causes changes in how the mariners are using that system. Right, the boats used to be able to get out through the breach, and now they're having to run all the way down along the south end. You can really see how sediment is falling out on the inside the bay itself as well, and kind of just filling in. And then it results in an additional breaching. So the image on the right, as you can see now, two breaches open around the spit that had formed and was kind of stable at the north end of all the other images. And then finally, coastal bank erosion. So coastal banks, you tend to see a lot of non-cohesive materials in the coastal banks. You don't see as much sands. And so again, you tend to see when the material erodes away from coastal banks, it's not going to come back. It's not windborne sediment transport. It was glaciation depositional processes. And so when the erosion hits these areas get hit the hardest because they don't have the ability to naturally come back in some sort of state. They do somewhat self-armor. As you can see, you have a lot of larger boulders and cobble and shingle falling out. And so those sediments begin to armor and provide protection in front, but they also are, they're just not enough in number to really play a role in the overall sediment transport regime. And then around structures, it's interesting. So the left image, it's two coastal revetments with an unrevetted area in between, and you kind of follow along visually with the top of the bank or where the top of the revetment sits. You can see how there's been a setback in between the two. So these two structures end up actually acting as a headland, and so it kind of creates its own headland space in between the two structures, which allows for the sediments to fall out and kind of a beach begins to form. But the only sediment supply for that beach is the erosion of itself and the upland area behind it. And so then, that area will end up being revetted in the future, and they'll probably bring it up to match the other structures. So it's just a continuous system. And then in other settings, you may have large navigational structures. So that imagery is the west end of the Cape Cod Canal, and that's the town of Sandwich. And so it's on the downdrift side of the sediment supply, and therefore it's slowly eroding away. And so what the Army Corps usually does when they come in to dredge the west end of the canals, will actually take the material and place it there in the nearshore area so that the sands can then move back onto the beach and provide protection to the homes in that community, as well as the other infrastructure in that area, including the marsh system, because the marsh system backs up to the downtown area of Sandwich. And so if that area floods, the water goes right into, actually the fire station sits right at the head of the marsh. And so the fire station has operational issues at many high tide events. Let's talk now about data sets. And so data sets come primarily from the federal government, are the ones we like to use because it's a consistent approach. The United States Geological Service has a coast and marine hazards and resources program. And through that, they've developed the Coastal Change Hazards Portal. And so the ability to kind of show you some present day storms, they show you shoreline change, and then they'll also show you sea level rise. But I'm primarily going to focus on the shoreline change portion of the tool today. The shoreline change, you have the ability to select both long-term or short-term data sets, as well as, of course, the historical shoreline profiles. Why is there a difference between long-term and short-term? So the data goes all the way back to the late 1800s, early 1900s, and they use what's known as NOAA T-sheets. So that was kind of the original cartographer's way of identifying where the shoreline falls. And then, in the 1920s and 30s, they began aerial photography. And so we started to get some observational information, but the photographs are not the best. People didn't understand how to take the great angles and what to look at. So some of the data through the 30s and 40s aren't the best. Then you start to get additional data sets. And now in the last probably 10, 15 years, instead of using photo imagery to determine where the shorelines are, we use LiDAR data, and we'll just use the elevation information from LiDAR to identify the 0-foot NAVD 88 contour. And that's what we use to represent as the shoreline within our erosion analyses. So those short-term data sets, right, you're kind of more comfortable with the data itself. There's less kind of accuracy, or there's less accuracy concerns with those data. Also in the short term, it's more representative of what's happening from a man-made perspective. We've been doing beach nourishment projects. So you're bringing sand into a shoreline. So, it might show a long-term erosion rate if you were using it. And then the short term, it shows the beach is being stable because they've been doing a beach nourishment project there. So it's good to understand the differences between the long term and the short term, and which one you should use if you're trying to do any kind of a design. It's important to utilize erosion rates if you're in the area and trying to understand where you're going to place infrastructure or where you're going to site a house, so do a residential construction. The FEMA's Residential Coastal Construction Manual gives a recommendation as to where you should locate a structure and have an understanding of what the long-term erosion rates are. How is this material provided? It's on a transect basis. You have the visual ability in this GIS system to kind of zoom in, and you can just see what the rates are. It's color-based. As a colorblind guy, it really doesn't help me too much sometimes. The gradations don't work too well. So what I luckily do is you have the ability to kind of subsample even more, and you can go to the source data and download it. Then once you've downloaded the data, you can bring it into your GIS, and you can look at what is the actual rate of erosion at that transect. And so that's one of the benefits of these data sets. Some of the challenges we have right now in the current administration is knowing whether or not some of these data sets will continue to be available in the future, as this site includes sea level rise, which is something that is being pushed away from the current administration's goals. Hopefully the shoreline change information will stay because it's still important for us in the design industry. So how do they determine this? They use a software that's called the Digital Shoreline Analysis System. It's actually just a GIS kind of application. And as I mentioned, you start with a baseline, and then you measure out to each one of the shorelines that you may have. And you'll notice there's uncertainty around those shorelines. As I mentioned, the 1800s, when you're looking at those T-sheets, you're not certain how well the cartographers are actually identifying where those spaces are. And then some of the older photos, because of the pixelation of the actual photos themselves or the flight elevations they took, you're not certain where they were identifying the shoreline. The other thing you realize too, of course, is that when you're looking at orthophoto, you're not really looking at the shoreline, right? More often than not, you're identifying the wetted line. So you're looking at the place where you see wet sand and dry sand, and you mark that as the shoreline. Well, that's not 0 NAVD 88 either. If you're trying to do an apples to apples comparison, you're identifying basically the point of wave run up at that day at that tide. So, as we've moved closer into the more recent photos, we tend to look now at what time the flight occurred. We kind of know the slope of the beach. We have a better understanding then of how far off our observational picturing of the shoreline is. So you can see that in the 1990s, you've got less uncertainty because you're more comfortable with understanding where the beach is. And then, of course, as I mentioned, in the more recent data sets, we're just using the actual LiDAR to determine elevation of 0 and AVD 88. But the important thing is we want to map them, or when we determine the rates, we want to do them in a linear regression. So, 2 points are perfectly fine to determine a line, and you can get the slope between those lines, and that's completely acceptable. We call that endpoint erosion. What's more preferred is to do a linear regression rate to determine your long-term erosion rate. And with that, then you just plot the position of the shoreline in relative to that baseline through time, and then you draw a best fit line through there, and then the slope of that line tells you what the rate of erosion accretion is. And so again, this is a standardized methodology that's being used throughout the United States, and it's greatly appreciated that the effort they've put into there. Another data set that the USGS provides is this total water level and coastal change forecast viewer. So this allows you to look at something instead of looking at it in a plan form, you're looking at it now in the cross-shore profile. So it's a 6-day forecast, right? So this is great for planners and community members who want to understand what's at risk in the future. I've selected a portion of the Outer Banks around where Highway 12 sits. For those not familiar with Highway 12 in North Carolina, if there is any type of higher wave energy, basically the dune washes over onto the road. They have to close the road for a day or two so they can get all the sediments cleaned up, dump back onto the dune, and then you're back to operating on Highway 12. So Highway 12 is just, you kind of go there all the time just to look at is when there's kind of waves spinning or some sort of weather spinning in the South Atlantic, because you want to see what's going to happen and impact there in the area of Highway 12. So it looks at kind of the impact and the overtopping rate of the beach. And so it's different than looking at, the plan form, which gives you rates. This is just giving you actual kind of almost instantaneous observational information of is my area at risk of being overtopped. And so it kind of helps understand erosion as well. States also one last one. Yeah. USGS also has HERA. This is a data set. I'm not certain how much longer this will be available for those of us to use. You can see it's not completely rolled out yet. It's kind of in California and Washington. It's also out in the Pacific Islands and territories of Guam and the Marshall Islands, and then kind of in the South Atlantic. But this is using the Cosmos model. So the Cosmos model is probably one of the better models that you can use that looks at kind of the evolution of a beach profile. So it's a way of looking at coastal erosion. And then what they've done then is they've taken the outcomes from these coastal erosion models over a multitude of tide ranges and also sea level scenarios. And then they've looked at different flood impacts based on the results of those models. So it's a great effort. But as I said, I'm not certain how much longer this remains based on the current administration. But it's a tool. It's interesting to kind of look at and see the potentials of how we can communicate at-risk areas to community members. And then states do this data work as well. So this is the state of Massachusetts Coastal Erosion Viewer. This looks very similar to what's available from USGS, and that's because the state of Massachusetts did work with the USGS in developing their data set. They actually paid USGS to do the work. but they wanted specific areas of the shorelines identified. So a lot of the USGS work is only looking at kind of open coastal flooding or open exposure. The state of Massachusetts wanted also understandings of its 100% of its shoreline. So they wanted to understand like within the bays, within the sounds. And so they paid additional to get more information. This too, again, is in a GIS viewer that you can zoom in. You also have the ability to download data, get the data on erosion rates per year. Again, also the short-term and long-term rates. So that's a great benefit. This is what it tends to look like. Again, so now I'm in the Chatham area again, the same area that we're looking at earlier with the barrier beach breaching. And you can see how they have actually also done the analysis on the inland side of the bay. So it's not just the barrier beach that shows whether or not it's eroding or stable or not enough information, but you can actually see what's happening on the developed part of the shoreline, which is the inland side of the bay. And so that's one of the reasons why the state had funded its own kind of study here, was to make sure that the appropriate awareness was being provided to community members living in erosive areas. Some states, though, also provide information about erosion because it's useful in a regulatory nature. So in the state of North Carolina, they have what's known as the oceanfront construction setback, and then that's based on erosion rates. So this is Wrightsville Beach. This is right when you come across the bridge, and that's Johnny Mercer Pier. So it's like right by the kind of the middle of the island. You have about 2 feet per year of erosion, or no, 2 feet per year. It's actually of accretion happening there. Part of that's because Wrightsville has a very healthy established beach nourishment project with the Corps of Engineers. So sediment's being brought in. So, it's not that you're seeing 2 feet of accretion. It's really just that the beaches are stable because the sand is being brought in on a semi-annual basis through beach renourishments. But the minimum setback factor as set by North Carolina law is a factor of 2. So they've got a table that says if you're going to build a structure less than 5,000 square feet, then your setback is a minimum of 60 or 30 times the setback factor. As I said, 2 is that minimum factor. And some areas of Outer Banks, your minimum setback factor is as high as 11 to 19, and other areas it might be 4 or 5. And that setback is based on basically an observation of the stable vegetation line, and you're going to set back 60 feet from that stable vegetation line. So it is something you have to do kind of when you're out there and look at your actual structure, but it is a regulatory requirement to kind of make sure that your home or any construction is not interfering with kind of the stable protective areas. Another state that uses erosion rates to help establish regulatory information is the state of Florida. They have what's known as the Coastal Construction Control Line. So it's not a regulatory line in the state in the framework of you're not allowed to build within that space, but it is if you are going to build seaward of the Coastal Construction Control Line, you must adhere to higher building code standards than you normally would have to. And what they've done in the state of Florida is you can see those red triangles. Those are range monuments. They do beach profile surveys offshore. And then, and it's not on an annual basis because there's just too much if you think of the state of Florida. So they just kind of keep rotating around the state, adding additional data to their data sets. And if necessary, and they see enough change in the inter years, then they make recommendations to move those lines. And so I highlighted this area. This is Lido Key. This is some of the area that was impacted recently when Hurricane Milton came through. But this control line's been in place the whole time. It's why many of those residential structures, survived the event. It's because they, built in accordance with the higher standards that are in place due to the regulation of this coastal construction control line. But there's also not just coastal erosion in a sandy nature that happens. Cliff faces erode, and quite often we see out in California, where slope face will give way, right, and it will block whether it's Highway 1 or it will block the Pacific Railroad that runs along through there as well. So the state of California has also grabbed some information to provide to homeowners, the rate at which the cliff face is retreating, as well as the rate at which the cliff top is retreating. So you can use this information when you're trying to do some siting. So again, this one's not regulatory. Again, it's just something that's provided for awareness for those wanting to live in these nearshore areas. State of Wisconsin has similar. They have bluff erosion rates. It's not available in a viewer right now because the viewer was provided through a grant that doesn't exist at the moment, so the data is not available. And then you have these, what are the mitigation actions we can look at for addressing coastal erosion? The common ones, of course, are the ones to think about. The first are retreat and setbacks. But there's soft and hard solutions. There's a unique observational information from sediment bypassing. And then I'm going to end with natural or nature-based features, which really are soft solutions, but just talk more about where we are headed as a kind of a group. So structure relocation is something that makes the headlines when it's the big structures that get moved. The images you see here are all moving of lighthouses. The image on the left is a lighthouse out in Nauset, which is the outer arm of Cape Cod. The middle image is the movement of the Gay Head Lighthouse. That's Aquina, which is the southwest corner of Martha's Vineyard. And then, of course, the image on the right is the famous Cape Hatteras Lighthouse when that got moved. And so all these structures, we build lighthouses to be visible, for mariners at sea for safe transit. So they had to be placed close to the shoreline, which meant they were in areas that were eroding. And then as this erosion happens now and the foundations are at risk, but we want to keep these historic structures, and decisions are made to move those structures, upland to provide protection. But at the same time, I'd say structure relocation is more in the forefront in discussions nowadays. We talk of it as managed retreat. And I think after Hurricane Sandy, and we saw the impacts to the communities on Staten Island and out in New York and New Jersey, the thought process has been, do we continue to keep our homes and our residences in place, or should we start looking at giving up these areas and moving away from there? It's something that's not been solved in any means. It's a hot button topic. Community officials don't want to see homes taken away because that's the tax base. And any homeowner doesn't want to sell their home because either they've lived there for a long time or, they rent the place out and they need that money, from the rentals. So yes, there's a lot of, you're not seeing a lot of structure relocation yet at the homeowner level, but it's definitely something I think we'll be seeing more and more in the future as the continuous rate at sea level rise is happening. I think there will be some untenable positions. We've seen it down in Louisiana with the Charles, where we've had to move a community to an area that's higher and out of the flood zones for them. Some of the soft solutions, dune plantings. So this is where companies go out and they are propagating, seed of their own grasses in their greenhouses, and then they bring those seeds out to dune nourishment projects and plant the dunes, or it might just be a dune that's kind of been denuded through time because of people walking through them, or it's been impacted by a storm, and so to increase the rate at which that dune could potentially grow, they'll come out and plant these plugs. You can see in the image on the right how gridded the plants are. So if you're on a beach this summer and you're looking up and down on the dune system, and you'll see the actual dune plantings and it looks gridded, then you can know that there's probably been a recent dune planting to kind of help resolve the overall impacts of the flooding and keeping those dunes stabilized. As I mentioned at the beginning, the roots help to keep the sand in place of the dune, and then the grass stems themselves act to drop the sediments out of transport in the wind, the aeolian transport. And then the grasses just kind of grow up through the dune sediments, and it's a good process. It's how dune heights grow. It's like as they continue to capture more sand, they can continue to grow in height, and then of course the higher the dune, the better the impact for storm resistance and flooding. You look at sand fencing. This is another kind of soft solution. It's a little bit harder because you're bringing out a material, but you can kind of plant it in a zigzag pattern, and the slats of the fencing actually cause the wind to fall out. In some areas, they're doing something called biomimicry. It's where they take basically wooden pallets, tear them apart, and they use the pallet wood because it's kind of cheap and easy to find. And you plant it vertically in an area where you want a dune to grow. And then as the sand falls out, you then come back out and you can kind of vibrate and you just rock the the slat upwards vertically, and then continues to grow the height of the dune. And so this biomimicry is something that was started on the outer edges of Cape Cod. It's happening now down in Puerto Rico because they don't have a large sediment supply offshore because of the coral reefs and how steep the features are, to how quickly you get to kind of 1,000 feet offshore. So by using readily available shipping materials, that's how they're trying to offset the idea of biomimicry. There's a beach dune nourishment database. So we've been doing soft solutions for a long time, nature-based solutions, putting sand on a beach. There is a database that exists out there from ASBPA, American Shore and Beach Preservation Association. I am the organization's treasurer, which is just make people aware. It's not an ad necessarily for this. It's how I know of this. But the idea is you dredge sand if it's in an offshore setting, or maybe it might be part of an Army Corps navigational channel, so it's beneficial reuse. And you're pumping that material then onto the beach. And then, as a friend of mine says, you're driving yellow steel in the salt water. And so, see these caterpillars in the nearshore zone pushing the sand up onto the dune, and then they'll form the beach behind it. But that's just one of the processes of doing these beach and dune nourishments. There's a lot of challenges with these processes. The sediments, there's only so many places you can get the sand from. It takes a lot of time to permit getting that sand out of that space. You're dealing with marine fisheries, and you have to do turtle exclusions and time of year limitations. So there's a lot that goes on, and a lot of challenges when you're trying to properly design and incorporate dunes. Some of the harder structures, we've talked about groins and revetments, and you can also build breakwaters. If you build the breakwaters close enough to shore, the sediment grains will fall out in the quiet loo behind the breakwater. And when those areas of sand move out to the breakwater itself, we tend to call those tombolos. So those tombolos, can act as like a groin themselves. Sometimes they'll actually build kind of breakwaters on the end of groins. They call those T-head groins. But one of the important things too, when we're looking at revetments, is your filter layers, making sure you have a filter fabric underneath it. In most, engineering designs, we use filter fabric to kind of spread the weight out of, the material that's on top. But we're not looking for that here. We want that filter fabric to kind of limit the amount of piping of sediment out from behind the structure. It's designed to encapsulate the material, but we need the water to come out because we can't let the water pressure build up to flip the rocks over. And so it's kind of like this basis of allowing porosity to allow sediments to move through. Sand bypassing, as I mentioned, it's really unique. There's only a couple places where it happens, but in these instances where sand is accumulated on the updrift side of a navigational structure, we'll kind of dig a hole and start to, suck the sand out of that hole and then just bypass that sediment to the south side. I think there's 2 locations where the plant is running almost, I think it's built in place, like they've got the pipes underneath the roadbed, and then it just dumps out on the other side. And then in other places, they'll bring dredges in, and they kind of do it on a temporary basis. So nature and natural-based features, this is really the big place where we're moving now. Again, since Hurricane Sandy, there's been a lot of discussion of how do we look at this. And, there's a project going on off of Stanton Island where they're doing a living breakwater. It's this idea of like you want to be able to let the natural environment reduce wave energy, and in doing that, there's potential then to grow natural features such as seagrass and marshes in the backside. And then those natural features can influence when storm surges come through and when wave energy comes through. And so there's a lot of these natural features that we're looking at and trying to incorporate in our design. But because it is so new, the community is developing, and so there's this network for engineering with nature that was stood up by the Corps of Engineers. That a lot of us in the coastal engineering community are members of this network. They offer free webinars, and then they've also got some really great podcasts. And so this is something that's just kind of the where the future is headed. Not to see as many of the gray structures, but as you can see from the idea on the right-hand side, they've got like reef balls in there, and so there is some gray. It's a gray-green kind of hybrid. We're not just seeing true nature at this point, but we're getting there. And so with that, I want to thank everyone for their time, and I appreciate it. And I believe we have some questions to answer, so we'll move to the Q&A.
Thanks so much, Brian. That was great. And we have, yeah, a few minutes for some audience questions, which have rolled in. Um, all right, let's get started with how does implementing nature-based solutions result in reduced erosion?
So the nature-based solutions, right? The idea is that they're working to like kind of, if it's a coastal forest, right? The mangroves specifically, the mangroves have like these dense root balls, and so they can actually limit the transit of wave energy. They can also actually impact water depth as well. So you're reducing the amount of wave energy that's causing sediment transport. So these, the results of nature-based solutions are really focused to reduce and limit the wave energies.
Okay. All right. Are there ways to design groins or other structures to prevent sedimentation of stormwater outfalls with the invert below the water level?
Well, that's a good one. It's actually something I'm working on right now. We where we actually have the center of the groin is actually the outfall itself. I mean, in this instance, though, it's because the groin field had been in place since the 1960s, and that outfall had always been there. So everything is it's in an equilibrium to that being in place right now. I would say there are ways to prevent it. A lot of it deals with kind of just any thought of how much velocity of water is coming out through the outfall itself. So it's pushing sediment away from the mouth. But you'd also have to look probably at the length of the structure. Yeah, the Indian River Lagoon is definitely unique because you have less wave energy through there. It's more tidal transport. So it'd be a different kind of look at it, but I'm sure there are ways we can look at it through what's happening through there.
Awesome. All right. Why would somebody implement short-term erosion versus long-term erosion rates?
So I think that's all the project need that you're trying to look at, whether or not you should look at both and then understand that the one is, goes back to the 1800s and there may be some uncertainty in the data that you're using. And then shorter term rates could be influenced more by, natural or man-made interventions. So there could be some beach nourishment processes that are happening in there that are throwing off the results a little bit. So you might not want to use the short term, or maybe you want to understand at least what it is between the two that you're looking at.
Sure. All right, moving right along. Given the combination of sea level rise, storm surge, and land subsidence along parts of the California Bay Area coast, what strategies do you see as most effective for balancing erosion control with the need to maintain public access and protect infrastructure?
Great question. I'm definitely, the Bay Area is so unique, right? It's like you have downtown San Francisco with all its vertical infrastructure and how they've built out in the Bay, but they're giving up Hunters Point, right? The Navy base that was there that's been going away, and so they're trying to turn some of that into a natural area. But again, it's going to be a challenge because some of the grounds are, I believe, contaminated, and so it's how do you work in those spaces? And then on the south side of the bay, you've got the old salt ponds that they're trying to return back to a more natural feature to allow the marsh to happen. There's going to be a lot of processes and procedures that have to put into place. I do think still continuing to use the gray and green process through there. Looking at ways to bring marsh plains back in. You're in most instances you have to go with the gray just because you need the strength to deal with the storm events that happen. But it's as often as possible, the designers are continuing to think of and bring in these green structures.
Sure. All right, we have time for one more. You see a lot of dredging along beaches to replace sand lost during heavy storms. Is this beneficial to the natural erosion process?
It's beneficial from the standpoint of the fact that more often than not, the sand that's being used is almost being recycled. So as kind of we talked about in those heavier storm events, the sediment gets brought into the offshore zone. And so what they're trying to do is target those spaces where the sand is, because it's whatever you put sand on the beach, majority of the time, the the local states have laws that state you must use beach quality sand. And so the beach quality sand usually came from sand that was pulled off the beach in the first place. So when they're doing their offshore, kind of resourcing, they find that this beach quality sand, if they put a tracker on it, it probably came from their beach in the first place. So it is a process of just kind of keeping the sand where it is. It's probably not the best tool, right? Because the natural erosion process would really allow the beach to roll back on itself as well. But we built too close to most of those barrier systems. And so, the tool we have then to offset that is basically to bring the sand back and put it back in its place.
All right. Well, I'm afraid we've run out of time for our questions today. For any that we didn't get to, we'll do our best to answer you via email. Just a reminder that at the conclusion of this webinar, you will receive an email with a link to download your certificate to use on Stormwater University or as a personal development hour for attending the webinar. Brian, thank you so much for speaking with us today and sharing all of that helpful information, and thanks to everyone for attending. Do not miss our final session, our closing keynote with Alexandra Cousteau. You can join that session by exiting out of this one and going back into the agenda and then selecting view for that closing keynote. So thank you so much, everyone, and thank you again, Brian.
Thank you, Katie. Thanks all. Appreciate it.